And we are live, hopefully. Hello, everybody, and welcome to another live streaming on assumptions of physics. And today we are going to see how we can essentially recover geometric structures starting from the entropy. So let's give a couple of minutes for people to join, and in the meantime, I'll start sharing things with this button. And there we go. Okay, so maybe I can give a summary of where we are so that we can, if people are joining for the first time, they can know what this is that we're doing. So the whole point of this work is to give a minimal set of axioms to describe statistical ensembles, with the idea that any physical theory needs to be able to describe statistical ensembles, because without being able to describe statistical ensembles, we can actually describe what we are getting experimentally, and we can't write laws that are testable and repeatably testable. So we have three axioms that we have. The first one tells us that the ensembles have to be well-defined experimentally. We need to be able to recognize one when we have it. And this basically means that we have a set of verifiable statements that we have shown in the theory, and so on. It basically means that we have a T0 second count topological space. That's basically the topology tells us what can we verify experimentally and what we cannot verify experimentally. Then we have the axiom of mixture that basically tells us that we have two ensembles, and we do a statistical mixture, we get another ensemble. And so ensembles give us a convex structure. And the third thing is that ensembles have an entropy, and the entropy quantifies the variability of the preparations within the ensemble, the instances in the ensembles, how much things jiggle around, let's say, in the ensemble. And it has some bounds. It has the entropy can only go up during mixture, so it's strictly concave. The entropy has an upper bound. When you make a mixture, it cannot go up, it cannot increase, can only increase up to this function I that we later, we previously derived to be the Shannon entropy with very general condition, and that things that are completely different from each other, we call them orthogonal, and we can see the two ensembles are completely different from each other simply because when we mix them together, they maximize the entropy of the mixture. So that's basically our three assumptions. We have a topology that represents experimental verifiability. We have a convex structure that basically represents the fact that we can mix ensembles and get other ensembles. And we have an entropy that quantifies how much variability there is in the ensemble. So only with those things, I think last time we went and look at the entropic constraint of the space, if I remember correctly. So we saw, is this where we stopped? If anybody was last time, but I think that this is where we stopped. We went through and we looked. Did we look? Oh man, I should have looked at the end of the previous videos to see exactly where we stopped. So
I don't know exactly, but we got to the point that there are constraints on the space because of the entropy.
right.
So we talked about vector space embeddings.
Okay, so we did go through the vector space embeddings. So yeah, so the title in fact says the entropic geometry. So we are here. So what we did last time, we showed that the entropy, because we have an entropy well defined, the convex space is actually a compact, is within a compact subset of a vector space. So it's very well constrained and behaved, and well behaved. And now what we're gonna see is that the entropy by itself puts essentially a geometric structure on the space that recovers the structure that we have in both classical and quantum information theory. So basically, this is a generalization of those structure and definitions in a way that we don't know that we have a classical space, we don't know that we have a quantum space. In fact, we could have a new theory because any theory needs to satisfy this, needs to give us ensembles, and so this should be valid for hopefully field theories and beyond. If somebody's doing quantum gravity, they should apply to that as well. So, as usual, we go through the text and see what it is that I wrote and see if it makes sense, go through the proof and see if they work and so on. Okay, so entropic geometry. We now show that the entropy imposes a geometric structure on the ensemble space. The core idea is that since the entropy is strictly concave, the Hessian is negative definite. And the Hessian, just as a reminder, it's basically the second mixed derivative of a function. You take the partial derivative twice, and now you have essentially a matrix with all the derivatives. The negation is therefore a positive definite real valued function of two variation and plays the role of a metric tensor. That's basically the whole intuition is that it's the strict concavity of the entropy that gives us a notion of distance and a notion of metric. So first, we're going to define this mixing entropy, and we'll see that it's going to be a pseudo-distance. The first observation is that the entropy can be used to define a pseudo-distance. If we mix two ensembles, in fact, the average entropy cannot decrease, and will stay the same if the two components of the mixture are the same ensemble. The increase then is zero if the two ensembles are equal, greater than zero if not, with the maximum if they are orthogonal. And orthogonal here means that, again, the two ensembles have all the instances of ensemble are so different that if you just saw one instance of one ensemble, you could say, I don't have the other. I must have the first. And this orthogonality is called orthogonality because it's going to recover the notion of orthogonality in both classical mechanics and quantum mechanics in terms of vector spaces. So the definition is, given two ensemble A and B in the ensemble space, the mixing entropy, also called Jensen-Shannon divergence, is the increase in entropy associated to their equal mixture. That is, if you take A and B, you take the entropy of the equal mixture of A and B, and you subtract the average entropy given by A and B. So you're seeing how much the entropy increase from the average entropy that you started with. And here we're calling Jensen-Shannon divergence because this recovers the Jensen-Shannon divergence, and we'll see later in both classical mechanics and quantum mechanics. Typically, the Jensen-Shannon divergence is defined as the symmetrization of the KL divergence, but it's the same as this. So that there is a relationship between all of this. Okay, so what we can show now is that the mixing entropy satisfies the following. It is non-negative, that is, if you take the mixing entropy of two elements, is always greater or equal to zero. And this just follows by strict concavity, because by strict concavity you have this relationship that the entropy of the mixture is greater or equal than the average entropy. So you put this on the other side and you get that the mixing entropy is greater or equal to zero. It has what is called the identity of indiscernible, that is, the mixing entropy of A and B is equal to zero if and only if A is equal to B. And to show it is just show that the concavity is strict, therefore this equality holds if and only if A is equal to B. Therefore, this is going to be zero if and only if A is equal to B. And then the mixing entropy is unit bound. That is, in unit of bits, it can only be one or less. And to show this, you just get the upper variability bound, which is again, it's the entropy of the mixture is less or equal to the Shannon entropy plus the average of the mixture. You take this, you bring it to the other side. So this has to be less than the entropy of coefficient 1/2, and that's it's 1 bit, and therefore this has to be equal to 1. So you have this quantity that is between 0 and 1, 0 when things are identical, and 1 when things are orthogonal. And it's symmetric, because by definition, if you look at by the commutativity of the mixture and by the commutativity of the addition, this is symmetric. So this kind of looks like a distance. It has some feature of the distance, but it does not satisfy the triangle of inequality, and that's why it's not properly a distance. The thing that is important to us is that both in discrete and continuous classical cases, the mixing entropy coincides with the Jensen-Shannon divergence, and in quantum spaces, it coincides with the quantum Jensen-Shannon divergence. And if you look up the definition, even just on Wikipedia, you see that the Jensen-Shannon divergence is defined, can be defined, can be equal. If you don't define it as in terms of the KL divergence, it has this relationship with respect to the entropy, and this is exactly our definition. And it holds the same in quantum mechanics. So we are essentially from a very simple starting point, we define something that sort of makes sense physically to define, how much things become, how much the entropy goes up when you mix two things, and you recover like an element of quantum information theory that is widespread. So what is important here is, as I said before, the mixing entropy fails to be a distance function as it does not satisfy the triangle inequality. Now, we know that it does not satisfy the triangle inequality because in the classical and quantum case, the Jensen-Shannon divergence and the quantum Jensen-Shannon divergence are the square of the distance function. So they're not the distance function, but there is a square of the distance function. And it is unclear whether this result can be generalized to the mixing entropy itself. So it could be that these things defined like this can be shown to be, in general, the square of the distance function, or it may be that it's only valid for those cases, or maybe you need an extra condition such that that is true. I have no idea. This is where this is for me is just a conjecture now. I just don't know how it works. So that's why it's research. We don't know everything. The lack of triangle inequality also makes it difficult to show that the topology is Hausdorff. The mixing entropy, in fact, allows us to create open balls around each point, and these open balls will shrink to each point as the radii goes to 0. However, one typically uses the triangle inequality to show that the open balls at some point become disjoint. So the point here is that there is typically a link between distances and metric to the topology of a space. Typically, what you use is you use the distance to define a base for the topology, and then you generate the topology from these open balls. And the open ball is basically the idea that you fix an epsilon, and then you take a point, you fix an epsilon, and you ask what are all the points that are within an epsilon of that point that you've chosen, right? So this essentially gives you a ball because it's sort of symmetric around that point. And see, an open ball, it's where you're asking for values that are less than the epsilon. It's not less of equal, but it's less. And that's going to be, you're going to say this is an open set in the topology, and then you generate the topology like this. Now, we know that because the entropy is continuous, this function is going to be continuous. And therefore, if you ask for, if you say all the elements that are between 0 and epsilon excluded, right, between 0 and epsilon excluded, that would be an open set in the topology of the real number. This is a continuous function, so you know that the reverse image is also an open set. So you know that these open balls are open sets in the topology of the ensemble space. What we do not know is whether those open balls are enough to generate all the other open sets. And we do not know whether you can essentially, whenever you have 2 points, you can make two open balls around the points, right? But you don't know whether those open balls are always going to intersect, or at some point when you shrink the balls, these balls are going to become separate. And if they become separate, your topology is Hausdorff, and this is important because if you have Hausdorff, then your limits are unique, and you have a bunch of nice properties. So this is where the connection between this and the topology could be done better. And again, right now, I don't have a good notion of how to do this. As we said last time, we know that we have an embedding in a vector space. We don't know that we have an embedding in a topological vector space. And the theory of topological convex spaces actually doesn't exist. I tried to find it and I talked to some people. Nobody actually gave me something that exists. So probably there is new math that needs to be developed here. And so that's the status. So, but if we were able to, for example, to show that whenever you have an open set and you take a point in an open set, you can always find an open ball that it's all fits inside that open set, that would be enough to know that all the open sets can be generated by the open balls. And so we know that this is the topology of the space. And this would basically justify why in math you always generate topologies from distance functions, because at the end of the day, when we're doing things in physics, that's exactly what we have, and the distance is defined by the entropy. So that's again a conjecture. Maybe it's true, maybe it's not, needs to be proven. Who knows? Maybe somebody who knows math better than me can do it. So that's the status. Okay, so that was for the distance, and now there is actually the more some more interesting part is that you can actually get a metric from that distance. And the idea long term is going to be to show that all the geometric structures in physics are actually a manifestation of this metric. In fact, I think I have a video going out today that talks about this relationship between entropy and geometry in physics. So that's basically the other intuition that we want to get, except from the other side, we're doing more the reverse physics approach, that we look how in classical mechanics and quantum mechanics, the entropy is the geometry. Here we're starting from nothing and we are getting some geometry out of just the entropy. And so we, at some point, we'll need to connect and make sure that those things are actually the same thing. Okay, so let's look at this. So the second observation is that the strict concavity of the entropy forces the Hessian to be negative definite. The negation of the Hessian then is a positive definite function of two variations. And in general, the Hessian of a scalar function is not a tensor, right? So the fact that you have this variational thing that you can define that it's positive definite is technically not enough to give a tensor. However, the ensemble space is a linear space, and that linearity has physical significance. It is only for linear coordinates linear with respect to the mixing coefficient that the convex combination of coordinates will equal the statistical mixture of the corresponding ensemble. Hi, Mark. So this is kind of an interesting bit. So in the ensemble space, in the state of statistical mixtures, there is some linear coordinates that are special. So when you typically do things on a manifold, you switch coordinates however you want, and no coordinate system is supposed to be more special than the other. And here it is not the case, because when you do a linear combination and these coefficients are probabilities, you are doing a statistical mixture. Now, if you had a nonlinear map between this probability coefficient and whatever variable that you had, then when you made the mixture, when you made the linear combination would not correspond to the mixture. You would have to take those coefficients, transform them into mixing coefficient, and then with those mixing coefficient, when you're doing the linear combination, you actually have a statistical mixture. So it is not the case that all way of charting things in an ensemble space is the same. The important thing is the linear combination, and this is the affine combination when you combine things and you preserve the linearity of the space. So it is only for coordinates linear with respect to the mixing coefficient that the convex combination of coordinates will equal to the statistical mixture of the corresponding ensemble. Therefore, the metric tensor corresponds to the Hessian calculated on that linear structure. Because if you weren't calculating on that linear structure, when you are calculating the geometry, you are going to make this convex combination to see how the statistical mixture work. And so you have to have a good definition of statistical mixtures. Otherwise, you're just saying nonsense. So therefore, the metric tensor correctly corresponds to the Hessian calculated on that linear structure. And when using nonlinear coordinates, as long as the coordinates are smooth, you can always make the appropriate transformation to the linear coordinate. So the fact that we have this linear structure that is important physically also justifies why we have a particular differential structure. And again, if you look at the details of the math, when you define a manifold, you say, I have a manifold, I have coordinates. And then you add this differentiable structure, and the differentiable structure tells you that these coordinates have they have to have the derivative well defined with respect to the other. But there are infinitely many differentiable structures that you could use and could define on the manifold. So the question is, why is it that you pick one? Which one is the physically significant one? And here we're saying which one it is. It's the one that it's differentiable with respect with the linear structure given by the mixing coefficient. So the mixture is really define the real structure, the real linear structure that we have. And then you can make coordinate transformation, but you also always have to remember that you come from that linear structure, and that linear structure is infinitely smooth because it's a line, and it represents line, and you need to be able to be differentiable with respect to that. So this sort of gives you some intuition as to why the mathematical structure has to be in a certain way and what it means physically. The issue here is that to do all of this precisely, it's still not clear to me what exactly the correct math is. And here I have a remark. In this section, we will assume that an ensemble space embeds continuously into a topological space, even though we have not yet proved it. So this is something that is still open. I don't know how to do it. And either it just comes out from the axioms that we already have, or we might be missing something. But I don't think we can do any physics if we do not have a topological vector space, because we're not going to be able to define variation. We are not going to be able to talk about these elements. I really think that we're going to have to, and so there's going to be some physical requirements that allows us to do it. We're going to talk about variation delta E on that space, even though it is not yet clear exactly which mathematical approach is best to make variations well defined. There is some literature when you do a sort of calculus on variation in terms of field theories and field theories or sort of optimization, right? When you make the entropy maximization or you use Lagrange multiplier, you typically have some topological vector space structure, and it's on that thing that you define the variation. But there are multiple ways to define them. There are multiple ways to define derivatives. I actually have another video in which I try to find what is the most general definition that we might have. And so there are all these little issues that, again, if somebody is interested to work on or knows more, that this is just an open problem to me of how to stitch it together. So for now, we're just going to say, we are going to get in the future somehow the idea that we have a topological vector space. We're going to make in the future well-define these variations, and we assume that this is already done. It's not already done. We still need to do it, but you have to start making all these pieces, and then at some point you're going to see how all these things connect. So we're also going to talk about a metric tensor, even though the space is not in general a manifold. And typically when you talk a metric tensor, you have manifold. So we're basically extending this idea of tensor with on calculus of variation, even though it's not really kosher, but whatever. We need something like that, even though we don't really have. So one thing that we say is that an ensemble space is smooth if the entropy is twice differentiable with respect to the mixing coefficient. So this is another extra condition that I don't quite know how to get right now. In principle, this is satisfied by both classical mechanics and quantum mechanics. And in principle, it will be satisfied by any ensemble space where if you have an ensemble that can be seen as a mixture of two things, then it can also be seen as a mixture of two orthogonal things. So if you can push everything, all the mixture, to orthogonal mixtures, like you can do in classical mechanics and quantum mechanics, then what happens is that the entropy is really the Shannon entropy, and the Shannon entropy is infinitely smooth. And so you do not have a problem. You're going to have this property. It might be that that condition of orthogonal separability is always verified because there is good reason to impose it. Right now, I don't see that we need to impose it, so I'm not imposing it because I don't want to inadvertently throw out good physics. I do think that it's going to work in field theories, because even in field theories, you should be able to make sort of distribution that are orthogonal at different regions of the field theory. So you should still be able to do that as well. The question would be whether, for example, if you want to do some type of quantum gravity, maybe that's not the case there. Maybe things become sort of so smoothed out that you can't really say, okay, these two things, I can perfectly distinguish between them, right? If the overlap in region of space is close enough, maybe that's the thing that might fail in some type of quantum gravity theory. So right now, I will just assume that the thing is smooth so that I can talk about essentially a Hessian of the entropy along this affine structure. So the affine structure gives us the differentiability of the space itself, right? We know what is how to make smooth variation on the space, but we still need that the entropy is smooth with respect to that structure. So for now, we impose it, and we have it. And then we can show, of course, that discrete and continuous classical spaces and quantum ensemble spaces are smooth. And the proof is straightforward in both discrete and classical case. And the quantum case, the entropy of an ensemble is the Shannon entropy of the decomposition in terms of pure states. And the Shannon entropy is a smooth function of the coefficient. So it works. And for the continuous classical case, the differential entropy is a smooth function of the probability density. Again, if you make a variation of the probability density, the entropy varies smoothly, which is a linear undermixture. Therefore, the entropy is always smooth with respect to mixing coefficient. And by the way, if you guys want to stop, have questions, and want to have the discussion on any of these pieces because you don't have the pre-requirements, you don't even understand what it is that I'm telling, you're welcome to stop in, and I'll be happy to talk about more in some of the prerequisites that one needs to follow this. Okay, so right now, what do we know? We know that we have an ensemble space where the entropy is twice differentiable, and then what can we do with this? Well, so definition, assuming that our ensemble space embeds in a topological vector space, now we can talk about a variation delta E for some definition. It sounds like there is a lot open for now. Yeah, so a lot of these details to make the mathematical framework, have all the details, they still need to be worked out, because we are going outside. So to make the bridge between the vector space, the convex space and the topological vector space, we are essentially going outside of the theories that are already well established. And so you need to define the mathematical theory, and that requires time, and probably will require somebody who knows the math better than me. So, I do what I can. Okay, So, unless otherwise noted, we assume the variation is expressed on the affine structure. That is, whenever we are going to calculate things, we are going to calculate them on the affine structure. It's not on a general structure. Note that it can be re-expressed through a nonlinear map as long as the map is differentiable. So you're going to be able to do map of the variation. So the typical thing that you do in calculus of variation, right? It's that you have a family of functions that is parameterized by some parameter, and then you take the parameter and you make it smaller and smaller, right? So that parameterization of the family is essentially kind of like a coordinate of a manifold, even though it's not quite, because it's not a manifold and it's infinite dimensional and so on. But it kind of should work like that. So you could have a family that has a sort of that follows a curve that is not linear in the affine structure, but then you are going to be able, if that curve is smooth, you're going to be able to define this variational derivative and be able to do things. So this is very much the angle that's probably too abstract for you and me. But the recent categorical notion of magnitude is being extended to also cover co-magnitudes, and apparently entropy falls afterwards. If there is anything that we can use and get results, I am, all open for it. The problem that I have with category theory is that every time that I look at a paper of that area, I understand like 10% of it, and here I need to understand exactly what are the links to be sure that the thing works. This is where I again, I tried to engage a couple of people from that camp. They didn't seem interested. If anybody knows of anybody that does category theory that works on these things, that is interesting to have a discussion. We can even have a live and go through these things. It would be actually interesting point. Next week, I'm gonna organize a live on a philosopher, a sort of an ex-collaborator of mine. We did a paper together on sort of philosophy of science and philosophy of physics, because he also, like me, like the spirit of this project is very minimalistic, and so he's trying to find what are the minimal things that you need to say or not say about metaphysics, such that you can have a reasonable understanding of what you're doing when you're doing science. And so we're gonna have a conversation about this topic, and I hope that we can like do more things like that in this channel, that we can get sort of expert in in a related field, and then start having discussion to sort of put all these pieces together, because here we're seeing that some pieces of math are missing, and we need to find them, and also the philosophy has to be done well, and again, otherwise we end up like the usual project where there is some physicist that doesn't understand the math of a philosophy well and just makes a mess of it, or a mathematician that knows the math and doesn't understand the physics and make a mess of it, and so on, right? We need to have the whole thing done well at all the different angles. So we're going to do that. It's literally a work in process. Okay, yeah, this is our work in progress too. The thing is that what is helpful for us, I think we have clear mathematical questions. So there are essentially two problems, right? One, going from the convex structure, the sort of this. First of all, is understanding what a topological convex space can guarantee you and not guarantee you. So, for example, simple thing like is the topological closure of a convex set in a convex space still a convex set? This is true in a topological vector space. In a topological vector space, if you take a convex set and you make the closure is still convex. I would expect this to work even in a topological convex space. It needs to be proven, right? So there are simple things like this that, quite frankly, They don't require even that much background, just require somebody that likes to play around with math and thinking about these things, which, most of the time that's what I do. And so that's one problem. Then there is the link of what are the necessary and sufficient conditions to go from a topological convex space to a topological vector space. And there, basically, you just need to be able to show that you have a continuous inverse. That's basically it. If you can show that the entropy is enough to have a continuous inverse, then that's basically it. We're done. We have a topological convex space. And I really, really think that it's going to be the case. Like intuitively, we should have enough things to be able to say that. Then there is the issue of whether the topology that we have is generated by the open balls of the mixing entropy. And if we can do that, we are great because we know exactly what the topology is. And then there is the notion of what is the right type of variation that we put on topological vector space. And that's a completely separate question. So even if you had just an expert that only knows about variational calculus and topological vector spaces, he doesn't need to know all the other things. So the point is that I am at the point whether I don't know how all these things streamline, I know what the pieces are. And so if I were able to find an expert in the different things, I would be able to ask the right question. And I'm going through some of these, not these particular things, but other elements I'm going to go through. I'm going through other mathematicians that are expert in other areas, and I'm trying to understand how that works. So for a question of spin, let's leave it at the end. Let's go through this because otherwise we're gonna context switch a lot. Like if we end, usually if we end like 10 minutes, 20 minutes before, and I don't think we have so much to go through. So let's keep that pin that and go that at the end. Okay, so where are we? We are assuming that we have proven that we have a topological vector space. We assume that we are proving that the entropy is smooth, and now we have these variations. And now given an ensemble E, so we take a point, we pick an ensemble, and then we make a variation on that ensemble. So an infinitesimal change on the ensemble. And now what we can show is that we can define a norm based on what we had before. We can define a norm on that variation. So Cram says, there is a small chance that at least the sum of the proofs I could handle if I'm given precisely what the pieces are. Like the convex topological vector space sounds fairly doable. Yeah, I agree. Like it's they are separated enough. So a topological convex space. So a topological vector space, it's just a vector space where the addition and the multiplication are linear function of the topology. That's it. There's nothing else to it. And so a topological convex space is a convex space where the mixture, where the convex combination is a linear scalar multiplication. You have a scalar multiplication and the addition. Both of them are continuous with respect to the topology. And that gives you, again, it gives you a lot of things. Now, if we want to extend this notion on the convex space, well, the convex space is going to be that when you do the convex mixture, then the convex mixture is a continuous function. That's it. There should be nothing else. And so it could be that the proof of is a convex, the closure of a convex set is still convex. It might be that you can even just look at a proof of how they do it in a topological vector space, and you say, wait a minute, the way that they're doing this is just doing convex combination. They're not doing anything else. I can take that proof and put it on the other structure. So something like f of axy plus bi is continuous if f of x and fy are continuous. Yes. because if f is continuous, then you have just combinations of continuous functions. Yes, that's exactly it. Yeah. Yeah, it's one of those simple things. So the thing that essentially we're missing when we go from the convex space to the vector space is that when you do a convex combination, you always go inside. So you have 2 points. So the convex combination is always inside. The affine combination, you can also go outside, right? And once you have the affine combination, you pick an origin, you have a vector space. So it's not it's not that difference. And so the question is essentially if you have a coefficient that you have a minus sign, right? When you make the scalar multiplication, right, continuous, you also have the minus sign there, right? And so that's basically what allows you to extend and go, past a set. Like if you can make a affine combination instead of just convex combination, so you have this minus sign, and you can prove that the affine combination is continuous, then that's it. The topological, the embedding topological vector, you continuously embed into a topological vector space. And again, I do not know that that's the case, so I can't say, oh yes, it can be proven and so on. But if it can be proven, probably it's not even such a complicated thing to prove. So it might be even a half a page, or it might be 10 pages because it gets horribly complicated, quite frankly. Sometimes the simple ideas are very, very difficult to prove. So, but anyway, so that's the key. It's very separate, and a lot of the math here is very separate. So if there is anybody that is going to watch this video that likes doing math, abstract math, and likes to play around with this, there's a lot of fun things to do. Some of the things that I have in this whole document were actually proven or helped proven by a first year undergrad, because there were some pieces of the math that already require some notion of topology and just some notion of set theory, which he had, and he was he was able to prove it. So yeah, so don't get scared. It's just and at the end of the day, you learn something, and instead of doing Sudoku, you play around with math. So okay, so going back, otherwise we're never gonna finish. So we have an ensemble space. We pick a point, we pick an ensemble, and now we make a variation, which really think physically as an infinitesimal change from one ensemble to the other. And then we want to ask, how big is this variation? So the way that we are going to define this size, this norm for the variation, is that we take the mixing entropy of the ensemble and the ensemble after the variation. So the initial ensemble and the other ensemble, and we ask how much the entropy goes up. And then we are going to take the square root of this 8 times of this. And you will see why we have this 8 once we go through the proof. Now we have a norm for the variation, and we can use this norm to define a metric tensor, to define some sort of inner product between two variations. And how we define it, it's the typical thing that one defines this thing. You take the square of the norm of the sum of the variation minus the square of the norm of each variation, right? This is sort of a triangle Pythagora-like things that you normally do in this. And then you stick a 1/2, because this is kind of like, you should think this as kind of like double the product of the two, right? So double the product of the two is the sum of the square minus the two squares. Like, this is how you do it. There aren't many other ways to do it. And what you can show now with this very simple definition is that the norm of the variation calculated on the affine structure is simply the Hessian minus the Hessian of the entropy applied to the same variation twice. And this metric tensor inner product type thing, it's minus the Hessian on calculated on the two variations. And now we're going to prove it, because the proof is so cool, because it's not very complicated. We're just applying things and following the math. It's it's this not even a page of proof that allows you to say, oh yes, from whatever physical theory we're going to have, once we have our entropy well defined, we have a geometric structure, which is super cool. Okay, so to recover the first two expressions, we simply have to calculate the leading term. And since the entropy is twice differentiable on the affine structure, we can expand it as the entropy of an ensemble plus its variation is the entropy of the regional ensemble plus the first derivative of the entropy times the variation plus 1/2 the second derivative of the entropy times the variation twice plus ordered or of higher order terms. This is just a Taylor expansion, right? There's nothing magical about it. It's just a Taylor expansion. So what we do is take this. Now we have, we go and take the definition, and from the definition, we're just going to substitute this and see what happens. So we have the mixing entropy that is from E and E plus delta E, right? Because this is what we define to be the norm of the variation, right? We just are calculating that. So we calculate the mixing entropy of the entropy and the entropy per se its variation. This is just the mixture of the two elements. So we are mixing E with E plus delta E, and we're calculating the entropy of the whole thing minus the average of the starting entropy. So the minus 1/2 the entropy of the first ensemble minus 1/2 the entropy of the second ensemble. Okay, so what we do here is just make the calculation. So this 1/2 E becomes E, and these are just copied here. And now we make the substitution in terms of the expansion. So here the original sample is E, the variation is 1/2 delta E. So this is the first derivative times the variation plus 1/2 the second derivative, the Hessian, times the variation square, the two variation, plus higher order magnitude. So this whole thing is the first term. The second term, there is nothing to expand, it's the same thing. The third term is going to be minus 1/2 plus the expansion of E plus delta E that we saw before. First derivative times variation, 1/2 Hessian, and then double the variation, and that's it. And then we start simplifying things. We can, this becomes 1/2, 1/2, 1/2, so this is 1/8, and it's here. And here we're just multiplying with this 1/2 here, 1/2 and C, 1/2 and C. This sum together to do minus and C. This minus 1/2 with the first derivative becomes this term. This minus 1/2 with this 1/2 becomes this other term. And then we have all the extra higher order term. The entropy goes away for the entropy. The first derivative of the entropy goes away with the first derivative of the entropy. Here we have 1/8 minus 1/4, and that's 1/8, and this is what we get. So we get minus 1/8 the derivative of the entropy. And now you can see why I had that 8 defined before, right? So then now we have the norm of the variation is 8 times the square of the normal variation is 8 times the mixing entropy. This 1/8 goes away, and we just get the Hessian minus the Hessian. Now, since we know what this is, we can go and substitute this norm inside the definition of the metric tensor, which was 1/2 the square of the sum minus the square of the first minus the square of the second. So we have this. We're just applying it here. Instead of delta E, this is going to be delta E1 plus delta E2 and delta E1 plus delta E2. This takes the first variation twice. This takes the second variation twice. And we have this minus sign from here. So this becomes minus, this becomes plus, and this becomes plus. And the Hessian is a linear structure. So the Hessian of the sum is going to be the sum of the Hessian. So you have 4 combinations here. You have E1, E1, which is this one, E1, E2, which is this one, E2, E1, which is this one, E2, E2, which is this one. And then you have, again, this side and this side that gets copied over. And yes, and I've collected the minus sign outside so that all the signs are flipped. I got a little bit confused. Okay, so this E1 goes away with the E1, E1. The E2 goes away with the E2, E2. This is symmetric. So this is twice delta E1, delta E2. It cancels out with the minus 1/2, and so we just get the minus of the S. And that's it. So again, what's cool here is that we are doing this calculation essentially without knowing whether we are in a discrete classical spaces, continuous classical mechanics, or quantum mechanics. Ideally, this should also work on field theory, except that I do not know exactly how you define entropy in field theories. That's another thing that is completely open for I don't know how you to define ensembles and entropy in field theory, but you must be able to, because otherwise, as I said, you can't do physics. And so it's very likely that this is gonna work. And so if we had all the mathematical structure well defined and nice and clean, we basically have a generalized a way of doing the geometry for these things. If we're doing this information theoretic things, that sort of works for us. And now the kicker is that we now show that this metric tensor we define reduces to the Fisher-Rao metric in the classical case and its quantum equivalent in the quantum case. So what we derived is not something that I come up with, from nowhere. This is the thing that is actually something used in information theory. It's sort of one of the basic tools that people use in information theory for both classical mechanics, classical information theory and information theory. So, can you apply concept to fine structure concept? Again, let's talk about these things later. Let's finish this because these are not related to the entropy. So let's go and look how this works. So for a classical ensemble space, the metric corresponds to the Fisher-Rao metric. And so we want to essentially show that we want to get the definition of the Fisher-Rao metric, and we want to get what we have, make the link to classical mechanics, and see that what we have reduces to the Fisher-Rao metric when we're using classical information theory. So that epsilon be a continuous classical ensemble space. Each ensemble space is a classical probability density rho. Let V be a manifold of a probability distribution over X parameterized by theta I. So this is the typical thing that you do in information theory. You have what is called a statistical manifold, and the statistical manifold is a bunch of statistical distribution with some parameters. So you could have the space of all Gaussian distributions, right? And the parameters would be, I don't know, the expected value and all the values for the variances and the covariances, right? That would give you a statistical manifold, right? Because it's a manifold because the number of parameter is finite, so there it's isomorphic to Rn. And typically this space of parameters is identified by theta. So this theta I would be all the possible positions, momentum, and variances and covariances of that. And you could do it for any type of statistical distribution. And the Fisher-Rao metric, when you have such a thing, is defined as minus the integral of essentially the mixed derivative of the theta I with the logarithm of rho with respect to rho. So you pick a distribution. From that distribution, you are going to have a particular rho, a particular density. And then you look at the variation of the density with respect to the parameters, and you calculate this integral, and that's the Fisher-Rao metric. That's what it is. So Fisher metric is defined as this thing, where log will be the natural logarithm throughout this calculation. So typically, we always said log was a log base 2, but in this case, people use the log e, And as we saw before, the change in entropy is just basically a rescaling. There is nothing else to it. And so it's just a unit change for our perspective. So I won't even bother to highlight the change in the logarithm. It just doesn't matter. Recall that for a continuous classical ensemble, the entropy is given by a minus the integral of rho log rho, right? So we now calculate the first term, two terms in the Taylor expansion around rho with variation delta rho, right? Because we want to calculate the Hessian, and how do we calculate the Hessian? By taking the distribution and making the variation. So recall that this is something that we're going to use over and over. The logarithm of x plus dx is the logarithm of x plus the derivative of the logarithm of x in dx plus 1/2 the second derivative of logarithm of x in dx squared. The derivative of the logarithm is 1 over x. The derivative of the logarithm is the derivative of 1 over x. So it's the derivative of minus 1 of x squared. And so this is the Taylor expansion for the logarithm. Okay, so we just take this and calculate the variation. Again, there isn't much can I say cleverness in any of this proof. Is just you just plug in the things, you calculate, and you magically get. Well, actually, here we're going to have to do some manipulation. But right now there is nothing. In the previous one, there was certainly nothing clever to it. Okay, so we have this. So we have the entropy of rho plus delta rho. So this is minus the integral of rho plus delta rho, the logarithm of rho plus delta rho. So we're just calculating. And we take from this, we just are doing the variation. So we take this and put it here. So we're going to have a logarithm of rho, 1 over rho delta rho minus 1 over 2 delta rho in delta rho. So we're just basically taking this expression, changing the x to the rho, and sticking it in. And now we make all the products. So the first order term, actually the 0th order term, with the one without the delta rho, is just this multiplied by this. So we have a rho log rho. So that goes in. For the first order, the one that has only one delta rho, we have two terms. We have this delta rho times logarithm. So we take the logarithm here. And then we have the 1 over rho multiplied by rho, which is just the constant one. And now what we do is take the second order term. The second order term, we have this multiplied by this, which is going to be this minus rho over 2 rho squared. And then we have the 1 over rho multiplied with the 2 rho. So we have 1 over rho minus rho over rho squared. And then we have higher order term. So this is just the same. This is just the same. Here we are making some calculation. The rho here simplify with the rho here. So you essentially have 1 over rho minus 1/2 1 over rho. So this is going to be minus 1/2 1 over rho. That's it. So we now know what is the entropy of essentially how the entropy itself what is the Taylor expansion of the entropy in terms of the variation, right? So this is the original entropy, rho log rho. This is the first variation, so this is the derivative. And this part here, this is the Hessian, right? So if we look at the Hessian of the entropy, this expression here without the delta rho twice, that's the Hessian. That's it. That's what it is. Okay, so we take this and we need to go from this to something that looks like this. And we are going to just use trickery, essentially. There are a bunch of mathematical trickery that people do in information theory, and this is one of them. So we take this, and the first thing that we do here is we add a 0. And the variation square, the second variation of a constant, is a 0. So this can be written as the second variation of 1. But the integral of rho over whole space, well, that's exactly the constant one. So we're substituting with 1 with the integral of the probability. Okay? And now, because this is a variation, we can take the variation inside the integral. And we can take this and put it together. So we have the -1 rho here, minus one. Oh, sorry, we do that, but we also now multiply by rho. So we put this together and we collect a rho outside. So the first term becomes -1 over rho divided by rho. So it's -1 over rho square with the variation square. With this part, now it's going to be 1 over rho because there is a rho here. So this is 1 over rho, the second variation of rho. Okay. And now what we see is that this thing, 1 over rho, is actually sort of the other way around. 1 over rho square is the derivative of 1 over rho. So what you have is that this thing in parentheses is just the variation of 1 over rho, the variation of rho. But then 1 over rho, the variation of rho, is the variation of the logarithm. And so now we have that the Hessian is the integral of rho on the x, the second variation of the logarithm. Yes, this is the tried and true trick of adding 0 and the tried and true trick to adding 1. Yes, it's exactly it. And I don't take credit for this. This is something that it's fairly standard in when you do information theory. There are different ways to express the Fisher-Rao metric. And there are trickery like this to express it in different ways. And that's essentially what I'm doing. I'm rewriting, I'm re-expressing in a different way, which is a standard way. Okay. So now this is, again, this derivation that we did, it's going to be true for any classical space where we just have variation. So we are in a classical space because now we know that these ensembles are distribution over some manifold, but we have done variation. So we have the whole space of all the possible statistical distribution. So now we consider a family of ensembles charted by a set of parameters, not necessarily forming a linear chart. So now we have now we have a manifold, right? Now we really have a manifold. And we are going to essentially express this general expression on the manifold. And so we are going to have this expression, which is the Hessian that takes the two variations. But now the two variations are a variation that can be expressed in terms of the coordinate of the manifold. So we're making a variation in the manifold. The variation in the manifold is going to make a variation in the probability distribution. And now the variation of probability distribution, we give it to the Hessian and you calculate things. And again, what we're doing is simply essentially applying the chain rule to this expression. And so we are just taking this variation is just going to be the second derivative with respect with the coefficient, then multiplied the variation of the coefficient, and this recovers the Fisher-Rao metric. So that's basically it. So the thing that we had before on a general space for in the classical continuum becomes the entropy. And do I say, yeah, so this is actually a proof only for the, this is why it's for a continuous classical continuous classical special. We should be able to do the same for a discrete. I do not know why I don't have anything here, but this is a to-do. Add a note proof for the discrete version. By discrete version, I mean the discrete probability distribution, not discrete. The variation are still, of course, on a continuum. Okay, so we have this, and okay. I don't know if there are any questions or comments. I haven't been keeping up with the chat because otherwise it's too distracting. Still gravity thing that we're gonna maybe discuss at the end. So let's continue on this. So for me, it's a little bit distracting if people in the chat are talking about everything. If they are too different, I won't be looking at the chat so I don't get distracted. So, but then it means that if people have questions for the discussion that I'm having, I'm not gonna see it. So I don't know how to solve that problem, but I'll continue. Okay, so now we should do the same thing for quantum mechanics. And in quantum mechanics, the situation is more complicated as there are different definitions of Fisher metric. This seems to be the state of the art. So I have two papers here linked, and you can see that there are different ways to express it. And I do not quite know, since the problem there is that you're doing essentially derivatives in the space of density operators, and it can get super complicated. I do not understand. And I don't know. We'll see the proof and look at how things work. All right. So for a quantum ensemble space, the metric corresponds to the Bourret metric and the quantum Fisher information metric. That's what we want to prove. So in principle, the Bourret metric should be something that is defined on the space of all density operators. And the quantum Fisher information metric is, again, the thing that you defined on a statistical manifold, a set of density operators that are parameterized by a set of... Okay, so that's one thing. Since we're working in a quantum ensemble space, each ensemble is a density operator rho. So now this rho is not a distribution over some manifold, it is actually a density matrix. And the entropy is given by the von Neumann entropy. So you have minus the trace of rho log rho. This is the expression of the von Neumann. So same thing that we have to do before. The thing is a little bit tricky because we are taking a variation of operators, and the orders matter when we are taking variations of operators, right? You can't just switch things around and do whatever you want. So you need a little bit more careful. So we have the variation of the entropy, which is good. So this is going to be minus the variation of the trace. We can bring the variation of the inside because the trace is a linear operation, and we can do that. And we still have the chain rule. So we are going to have that there is the variation of rho times the logarithm plus rho, the variation of the logarithm. Okay? This in general, right, it's different. Like we can't just put the variation afterwards. The variation is in front. These are operator. You can't just commute. These things don't commute, right? So this is how it should work. Then the variation of the logarithm is the inverse times the variation. So we can do that. The inverse is before. Now this variation is multiplied by this other, the inverse is multiplied by the rho. So this becomes the unit. That's fine. And now, because we are under the trace, and the trace has the cyclical property, we can take this and bring it on the other side. So it is true that the trace of A times B is equal to the trace of B times A. So we are not commuting, we are using the trace property of the cyclic property of the trace and bringing this on the other side. And now we can write this and we're good. Now, taking the second variation, again, we have this expression, we take the variation, we can again take the variation and bring it in. And again, we can use the chain rule. So we have the variation of the first term plus the variation of the second term. And now I'm a little bit confused as what's going on here. Shouldn't I have a logarithm of rho plus 1 beforehand? And this is great. I can't even understand my own proofs, but I guess that's why we're going through them in detail. Okay, so what is happening now? I'm taking the variation of the first, then I should be taking the variation of the second. There should be a logarithm of rho plus 1 over here. Absolutely stamped.
I mean, you
Fantastic.
can forget about the one, right?
Say it
When you have
again?
a variation, you can of course forget about the one. When you vary log rho plus 1, maybe you already simplified in one step.
I've already simplified in one step. What did I
Maybe.
simplify?
I don't know. If you take variation of log rho plus 1, you would get variation of rho divided by rho, I guess.
Yes. Yeah,
Yeah.
I'm sure that this thing is gonna work. It's just I'm confused as to because here I'm actually making the calculation to show that this thing becomes this thing. So again, I would have expected that I made the variation of the first and the variation of the second, and then I have this multiplied by logarithm of rho plus 1. So I wouldn't only have this, I would have a plus logarithm of rho times the second variation, right?
No, yeah, you're right. So you don't vary log. I got confused as well. Yeah, you should have the bracket in front, yeah. But doesn't matter since the term is 0 anyway. If you multiply it by anything, it will still be 0, right? You throw away the second variation of rho.
Say it again.
You throw away the second variation of rho because it's linear in the chart anyway, and you just forgot to multiply it by something. But who cares? If it's 0, doesn't matter what you multiply. Does it make sense?
I'm not following, sorry.
You just forgot the factor log rho plus 1 in front of the second variation of rho.
Correct.
It's just missing.
Yes.
But if you just add it in like 2 steps, you will throw away that term anyway because it's 0.
Oh, okay.
Does it not make sense?
Yeah, I must have got it when I wrote the thing, and it seems so obvious that yeah, so we should definitely add the line because if I can't like reconstruct it,
No,
and I
definitely.
wrote the proof, that's
Put
pretty
put
bad.
in the
So
log rho plus 1.
okay,
It's
so
missing.
let's do it. Let's fix this. Oh man. Okay, so so much fun. Okay, so we have this, right? Did I copy and paste the right thing? Okay. So we have this, and here we have this part, right? In here.
Yeah, but I would simplify this later because it
Right?
only simplifies because it's 0. Like the rho is 0.
Oh, okay. I wrote it here. Okay, so it doesn't matter. That's what you're saying. It doesn't matter what I multiply here because it goes
Yes.
away. Okay, yes, sure,
Actually, all
sure.
the lines are true. It's just you could put anything in front.
Yes. Okay, thank you. I got scared for a second. Okay, so there you go. So we have this, and okay. So I don't need it to put it twice. Actually, I just need to add it, and that's it. Okay, okay. Very good, very good. Thank you for the help, for the assist. Okay, so we have the variation of this thing. So now we have the variation of the first plus the second unvaried plus the first unvaried variation of the second. And then when we're making this variation, we have the logarithm, and it's going to be 1 over, like it's going to be the inverse of rho times the variation, and the variation of 1 is going to be 0, so that goes away. So now we have this. And now, because the variation rho is defined in a linear chart, as we did before, we said before, this thing is gonna go away. It's 0. And so the only thing that remains is minus the trace of the inverse of rho times the two variations. Okay, good. Which is the same thing that we had here, right? So note the absolute equivalence of what we had in classical space and what we have in the quantum space. It's just that instead of doing an integral, we are taking the trace. And that is considered a family of ensembles charted by a set of parameters, not necessarily informing a linear chart. We have the metric with respect to the two variations, two differentials of the parameters, and we're doing the same thing that we did before. We're using this variation with this differential to calculate the variation on the density operator in this case. And so what you're going to have is that you're going to have the partial derivative of the density operators with respect to the parameters, and the trace is a linear chart, a linear function, and so the differential can go outside, and this is exactly it's one of the version of the Fisher-Rao metric. It's one way that the Fisher-Rao metric gets expressed. Now, there is another way that it's in terms of the right logarithm derivative. And if you have never heard of the right logarithm derivative, it's I never heard of it either before I started looking at these things. But basically, LR is an operator that satisfies this equation. It's a solution for this equation. And I, quite frankly, don't know exactly why it's called a logarithm derivative. If you go to Wikipedia and some other text, they tell you that, oh, yes, because you can think it. I couldn't understand an intuitive I don't have an intuitive understanding for this. For me, it's just the operator that solves that equation. So I don't quite know what more I can say about that. But what you can do is take this and essentially substitute it in the expression that we had before. And what you're going to have is you're going to have rho minus 1, and you substitute with these two things. And again, now this is going to cancel out, and you see that the rho is in the middle, but because the rho, it's the trace, it's cyclical, so you can move this in front. And then because then the operator is symmetric, you can reswitch the i's with the j's. And so the net effect of all these things is that you took and put and brought the rho in front. But you're not just doing the commutation, you are applying all these rules. And this recovers what is called as the RLD Fisher information. And There is also something else called the Ruppenier metric, which is the Hessian of the entropy. And there is also some stuff called on the Hessian metrics defines in Hessian structure. So there is probably other related math that works for all these things. And so again, there might be a more richer literature that one can connect to. So this is basically it. We went through these proofs and we fixed something, which is always good. And so that basically the overall point is that starting from just the entropy, we can define these geometric structures. And one of the interesting bits is going to be that we should be able to then use this geometric structure and then project it in the space of phase space, which is going to be something that we should be able to recover from the ensemble space. It's related to the Fubini study measure, which is the measure that you put on the geometric structure that you put on the space of pure states of quantum mechanics, that is related to the inner product itself, and the inner product in quantum mechanics defines the entropy, and so on. So what needs to be, what I know that can be done for sure, and what needs to be still done in the details is sure that this structure is basically, it defines all the other geometric structure that we have in physics, right? And we need all the other construction to lead to this. But that's basically it. So that's as much as I wanted to cover for today. If there are any questions specifically on this, let's start with those.
So the right logarithmic derivative, it just looks like if you would invert, like if there is a row inverse, which in our case should exist, it would be just what you naively would guess, right? It's 1 over row, and then you take the derivative. Like there's just a chain rule of taking like derivative or something in a log, right?
I think so. And I
Yeah.
think it might be used for those cases where you can't really take the inverse of the matrix.
Yeah. Or maybe, I don't know if it would be, it's a chain rule, right? Maybe there is also an ambiguity of whether you put the operator left or right. Like if you
That
take
there
the
exists
chain rule,
because there is also there is a symmetric logarithmic derivative.
I would guess there's also a left one, right? Where you just swap the order.
I seems to that the left one seems to be less used. The two ones that I found in the literature the most was the right and the symmetric one. I don't know
Yeah.
why the left is less used.
Yeah. But I can see that if the inverse exists and they all commute, I would get what I naively would expect. So it's not completely arbitrary.
Yeah, and I don't think it's arbitrary either. It's just
Yeah.
that yeah, the thing that I think, as I was saying before, I think this is very important when these matrices are have a zero determinant, because then you're not going to be able to make the inverse. But in
Can we
our
have a
case,
zero?
go ahead.
We can, right?
Well, what?
Can we have a zero determinant?
We can't, because these are density matrices. So the density
So
matrix,
if if they're not completely trivial, yeah, they will have some zero eigenvalues,
they
right?
have some zero eigenvalue. Yes, yes, yes.
Okay, yeah, then it definitely makes sense, and we need to be careful.
Yeah. But again, so this is the thing that it's that I'd like, if somebody knew these things better, I could, because we, like a lot of these properties that we use within this these calculations are not valid in general, but they're magically valid when you are inside the trace. Because you're looking for the trace, there are a lot of things that you can do that you couldn't normally do, like swap operators because you have the cyclic rule, and do a bunch of other things. And I feel that some of these things also apply when, for example, you're doing expectation values. Expectation value, you're going to have a trace operator. And so there must be a set of property. Like, it would be nice to have a complete set of properties that are valid, that are not valid when you're doing normal things in linear algebra, but when you're inside the trace, then this become valid. You know, I just don't know them. Anything else about this? Okay, so let me catch up on what was discussed here. I just understand. Okay. Yeah, so okay, so the question like this, about spin or whatever, or other things, I'm happy to answer that, but please let's keep them at the end because otherwise it becomes too disruptive. And yes, the spin is an intrinsic angular momentum. This is where certain technically this is what I said. I don't know if you're referring to a regional two-level system on quantum computing, but spin is defined as an angular momentum. It's simple learning, but I can share that it's not wrong. You don't have So yeah, to me, spin is also it's the intrinsic angular momentum. The way that I think about it, I often talk about it as a directional degree of freedom. I just posted a video last month with the idea that directional degree of freedom has to be three-dimensional. In quantum mechanics, the directional degree of freedom is spin. It's an angular momentum in the sense that the state is defined by essentially a direction, and the geometry that you are representing are directions, and it's intrinsic in the sense that it's not defined at 2 points. It's defined at a single point. So it's something that is carrying a direction, but it's your infinitesimal particle. It's one thing on which is defined. There are still many things that I don't understand about spin. So I don't understand exactly the space of relativistic spin. I do understand it kind of in classical, the classical version of it. I understand better than the quantum version. Like there is something that the thing that I don't understand of relativistic spin. Again, I'm saying it here in case that anybody can give me an idea, but I have never found it in the literature. So in principle, all how can I say? Degrees of freedom are symplectic, like they're symplectic structures. So you have pairs of variables, and you have, if you have a non-relativistic spin, your pairs of variables are the angle on a plane and the vertical direction of spin. That's basically it. That's the spin. In relativistically, what is the analog? What are the conjugate variables that you can use to describe this directional degree of freedom, which now is not just a direction, but it's going to be a direction and a boost, essentially. And that part I still haven't found. So if anybody has ideas for that, I'd be really because because I would need that to understand essentially the spin statistic theorem, which is still something that I don't have a good intuition for. I think nobody does. So I don't know if any of this answers Christian's answer. I don't even know if Christian's question, I don't even know if he's still on, but I don't know what more he wants to know about spin. Anyway. And thank Verbalion for trying to answer. It's just that it got a little bit too long. I'm not very good at just going forward with things if there is activity in the chat because I feel that I have to look. But maybe it's just me that I have to go over it and not do it. I don't know. Anyway, any other questions? Otherwise, we just call it a day. Going once, going twice, going three. Okay, so we'll close it for today.
Yeah, I don't
Bye.
have anything else.
Okay. Next time, we are gonna probably look, I still need to review this, but we're basically going to look at a generalization of the Liouville measure, and that's another thing that again is gonna be another thing that sort of appears out of nowhere by making simple things and simple machinery, simple definition around the entropy, and you get things that it's still interesting. So it's always cool. Okay, so thank you everybody for bearing with me for this hour and a half. See you. No, next week I'm not gonna be here. I think I have something, so I'll post a message on YouTube. But I think we have to cancel for this for next week and do it in 2 weeks. So see you next time.
All right.
Bye.